Hi everyone. So we just finished covering the simple example of a coin flip, defining sort of a prior for a very simple example. In this case, we sort of developed the beta distribution prior and then multiplying it by the Bernoulli product, which eventually became our likelihood. And so by multiplying our prior by likelihood, we obtained an object which is proportional to our posterior, and talked a little bit about maximizing that object and what we got as a result. Maybe there's a couple of things we can say about so now that we've discussed basic language, there's a couple of things we can say about sort of the philosophy of Bayesian methods. So the first thing I'd like to do is sort of to write something down and ask us to consider it for just a second. What is the meaning of this object here? Well, this object is the probability of the parameters given the W divided by the probability of a different parameter given the W's. So this is really a ratio of posteriors. So sometimes we may not want to maximize posteriors. Again, if we're maximizing posteriors, it kind of becomes equivalent to maximizing the likelihood. So normally speaking, we may not want to do something like this, but perhaps we may not want to sample from posteriors. Instead, we may want to sort of compare two different hypotheses. And in this particular case, we may want to ask, well, let's compare the probability of some parameter given the data as compared to the probability of a different value for that a different numerical value for that parameter given the data. So this can be actually a very useful quantity to compute, just as a means of hypothesis testing. Here's another one, and there's an infinite number of them that we can write down. Whoops. But here's another one that's kind of useful to write down by the time we've been able to write down our posterior. So this is kind of a ratio of probabilities over some range A versus a range B. So you may want to ask, for example, is there a trend in my data? Or how probable is it that the parameter be greater than 0 as compared to this parameter being less than 0? So by integrating over a different range of the parameter, and again, these don't need to be one-dimensional integrals. You could have very many values for, you can have a very high-dimensional posterior. You could be considering sort of volumes. How probable is it for the collection of parameters to be assigned range, values between this numerical and that numerical value as compared to some other range? So those are objects that we can start constructing given our posteriors. We can construct ratios of likelihoods as well. There's nothing wrong with that. It's asking a slightly different question. And this question pertains to, for example, how probable is my data given some numerical value for the parameter as compared to how probable it is, or how probable the data is to have been generated given a different numerical value for my parameter. So there's an equivalent object here that I can construct sort of in comparison to sort of the ratios of posteriors. This one's a lot harder to do when it comes to likelihoods, because the likelihoods, it doesn't make physical sense to integrate a theta for a likelihood. In contrast, it does make physical sense to integrate a theta when you're working with the posterior. So here we're basically asking a ratio of how probable sort of a range of parameters is. Especially if parameters are sort of continuous quantities, like probabilities of heads that are continuous between 0 and 1, or diffusion coefficients that are continuous from 0 to infinity. Sometimes it's a bit of a strange question to ask how probable is a diffusion coefficient or a probability of heads, let's say, of 0.50000 1 as compared to a probability of heads of 0.4789624. Right? We may kind of want to consider ranges instead, which is to say, what is the probability of heads greater than 0.7 versus anything below? Because I have an inclination that it may be sort of biased towards high values. So those are the kinds of things that we can do with posteriors. Another thing we can do with posteriors is build something called a predictive distribution. And the predictive distribution is as follows. It's the probability of wn plus 1 given w1 to n. I would say that this is an example of a predictive distribution. Another example of one could be n to m given w1 to n plus 1 to n plus m, so some future range given the previous results. So the question is, how do I go about constructing? And let's work with the simpler one, and everything that I say generalizes to sort of predicting a range of data. How do we go about constructing this? Well, we need to build our posterior. So we have the wn plus 1 given theta multiplied by the probability of theta given w1 to n. This here is the posterior. This is the likelihood of the n plus 1th data point. The point in constructing the predictive distribution is that now I need to be able to marginalize over this theta. And marginalizing over this theta may or may not be a simple integral. Let's go ahead and sort of develop an example of where we can sort of build a predictive distribution for the case of not just a coin flip, but something where we have very many options. Now, before I go any further, let me just say one little thing, or before I discuss this example, let me just say one little thing about this predictive distribution. We notice that we're marginalizing over all values of theta, but we need to be a little bit careful because whenever we build posteriors, in some sense we're always conditioning, without saying so explicitly, on the model itself. So while the predictive distribution may not depend on the numerical values for the model parameters which we're integrating over, it may depend on sort of the mathematical structure, and it will depend on the mathematical structure of the model itself. So, for example, when I had a coin flip, I had assumed Bernoulli draws. That's a model. So while I'm learning the pi, the probability of heads for the Bernoulli draws, I'm not necessarily sort of learning what model is involved. Now, in more general Bayesian applications, when we start discussing Bayesian nonparametrics, we may start relaxing some of these conditions and start saying something about the model and more precisely the dimensionality of the model. But until then, whenever we're doing calculations, whenever we're doing any kind of Bayesian calculation, we're trying to learn distributions over the theta, but the assumption is that we're never really touching the underlying model. We're learning parameters about that model, but we're never touching the model. Similarly, when we construct predictive distributions, this is always, to be very precise, kind of conditioned on the model that we are not touching, at least in the current context. So let's go about doing an example for constructing predictive distributions. And let's start off with one where we have 3 options. So rather than a coin flip, we're going to have 3 possible options. And the probability of the data here will be pi 1 raised to the delta 1 wn, pi 2 raised to the delta 2 wn, and then pi 3 raised to the delta 3 wn. Now, just like with the coin flip, where pi 1 plus pi 2 is equal to 1, then similarly here, pi 1 plus pi 2 plus pi 3 should be equal to 1, because the sum of the probabilities for each one of my outcomes needs to be normalized to 1. Now, I can go through the same exercise that I did before and verify that my P of W is indeed normalized with respect to W by considering all three options. Right? So I have to remember that this is my likelihood for one data point. And that likelihood is normalized with respect to all three options. Option 1, option 2, option 3. So let's go ahead and define a prior. And that prior, I'm going to write down, there's a normalization constant. And it's going to be, and again, we'll discuss how to set these priors shortly, but it's going to be pi to the alpha 1 minus 1, or pi 1 to the alpha 1 minus 1, pi 2 to the alpha 2 minus 1, pi 3 to the alpha 3 minus 1. This distribution has a name. It's called a Dirichlet distribution. It's, in this case, a three-dimensional distribution. Its variables are pi 1 to 3, and its parameters are alpha 1 to 3. So just like we write down the normal distribution, x colon the mean, comma, the variance, here the x, or the variable in question, are the pi. So it's a distribution over the pi's, these probabilities. And then the parameters are these alphas, alpha 1, alpha 2, alpha 3. Later we'll be discussing sort of the effects in the Dirichlet distribution of these pi's. Now, if I multiply the Dirichlet distribution by my likelihood, especially a likelihood involving very many draws, so have a W 1 to n, I will notice that my posterior will also be Dirichlet. In fact, for the previous example that we had considered when we had two options, a coin flip, we noticed something very special, that by virtue of choosing a beta prior and multiplying it by the Bernoulli likelihood, we obtained a posterior, which was also beta. In this case here, in a slightly more general case, we're going to explore the fact that our posterior will in fact be Dirichlet. But let's go ahead and write down how we would find this normalization. So P of pi 1 to 3, we said is equal to pi 1, alpha 1 minus 2, pi 2, alpha 2 minus 1, pi 3, alpha 3 minus 1, divided by 0 to 1, d pi 1 to 3. Then I have the stuff in the numerator, which I can write down. And then there's an interesting condition. I know that the sum of the pi's, pi 1 plus pi 2 plus pi 3, must be equal to 1. So this delta function condition actually, and this is a Dirac delta function, is very important towards taking this integral. Now, if you take my word for it, I'm going to go ahead and write down what the integral here is, and it's alpha 1 plus alpha 2 plus alpha 3 divided by gamma of alpha 1, gamma of alpha 2, gamma of alpha 3 multiplied by, and that's the normalization, the remainder, the relevant, the pi-dependent portion of my Dirichlet distribution, which is this quantity here. This is my normalization. And these gamma here's, these gammas are gamma functions. So, now that I've done this, and I should also say the gamma function, well, let me do it on the next slide. The gamma function, gamma n, is defined as n minus 1 factorial. In other words, n minus 1 times n minus 2, dot, 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 all the way to 1. The gamma function technically is a little bit more general because it can treat sort of fractional factorials that I cannot write sort of in this very simple form. But that's almost an aside here. Okay, so now let's go ahead and write down the predictive distribution. For example, what is the probability that wn plus 1 be realized to the first option given all of my previous findings, all of my previous w's? Well, that's going to be equal to the integral of pi. I just have to sort of by hand impose the fact that my pi sum to 1. I don't have to do it. I can choose to write down every time I see a pi 3, just like I did with the coin flip, I can choose to rewrite pi 3 as 1 minus pi 1 minus pi 2. But if I choose to write down pi 3 explicitly, then I just have to account for the fact that pi 3 is constrained by virtue of this relation that the sum of the pi's must be equal to 1. And then finally, I have the multiplied by the likelihood this is pi 1 to 3, multiplied by the posterior, which is pi 1 to 3, given w 1 to n. So now we can ask ourselves the question, can we construct this? Can we construct that? Yes, we can. This is the prior multiplied by the likelihood. This here is simply the likelihood. This term here will be the simplest. It's simply going to be pi 1 raised to the 1, because it's the probability of observing the first outcome. This term here will be quite simple. It's going to be, well, proportional to pi 1 raised to the number of outcomes that I have observed in my from my first option, plus alpha 1 minus 1, multiplied by pi 2, n2 plus alpha 2 minus 1, multiplied by pi 3, n3 plus alpha 3 minus 1. And of course, the proportionality I can work with because I know already how to normalize the Dirichlet distribution. If I notice I have a pi 1 raised to the 1, and I have here a pi 1 raised to the n1 plus alpha 1 minus 1. So the 1 and the minus 1 cancel. So if I were to rewrite this entire integral here a little bit more neatly, then I would have, and writing out the normalization for my posterior as well as a prefactor, I have gamma of alpha 1 plus alpha 2 plus alpha 3 plus n here being n1 plus n2 plus n3, the sum of all three outcomes. And then I have gamma of alpha 1 plus n1, gamma alpha 2 plus n2, and then gamma alpha 3 plus n3. And here I multiply by this integral. I still have my delta function that I won't write in full. And I have my pi 1 raised to the n1 plus alpha 1, multiplied by pi 2 raised to the n2 plus alpha 2 minus 1, and pi 3 raised to the n3 plus alpha 3 minus 1. Now, let's ask about this normalization constant. Where did that come from? Well, I said I normalized my posterior, and my posterior is a Dirichlet distribution. Okay, I knew how to normalize my Dirichlet when I had an alpha, pi 1 raised to the alpha 1 minus 1, multiplied by pi 2 raised to the alpha 2 minus 1, and so forth. Here, I basically have exactly the same thing, except rather than being alpha 1, alpha 2, alpha 3, it's n1 plus alpha 1, n2 plus alpha 2 minus 1, n3 plus alpha 3 minus 1, and so on and so forth. So the normalization is indeed what I've written down here. Now if I look at this integral, what do I notice? Well, I notice that this is basically the exact same integral that I need to normalize the beta distribution again. So if I just look back at the definition of my normalization, of the Dirichlet distribution, sorry. So if I look back at the definition of the normalization for my Dirichlet distribution, I find that this here is the answer to this integral can be immediately written down. So I have a normalization here, and I'm going to have another integral here that I can immediately evaluate by just looking at the normalization. So what we have is p of wn plus 1 given, equals 1 given w 1 to n. And we know that that is going to be equal to the product of the original normalization that we had, alpha 1 plus alpha 2 plus alpha 3 plus n divided by gamma of alpha 1 plus n1 multiplied by gamma of alpha 2 plus n2 multiplied by gamma of alpha 3 plus n3. And all this multiplied by the result of the integral, which comes from basically looking at the definition of the normalization for the Dirichlet. So it's going to be alpha 1 plus n1 plus 1 multiplied by alpha 2 plus n2 and gamma of alpha 3 plus n3 divided by gamma of alpha 1 plus alpha 2 plus alpha 3 plus n plus 1. So we remember that gamma of n is n minus 1 factorial. And that's going to simplify this result dramatically and in fact give us a result that we sort of would have expected. We're not seeing it yet, but let's go ahead and do it. So this cancels with that, and what we're left with is these four terms here. And if I did my math correctly, and using the definition of the gamma function, the simplification of these terms should be alpha 1 plus n1 divided by alpha 1 plus alpha 2 plus alpha 3 plus n. If all of my alphas are 0, then this is n1 over n. So let's just try to interpret this result for just 1 second. We're saying that the probability of observing the next data point given all of the previous ones, and I should back up, the probability of observing the next data point in the first category given all of the previous ones is simply equal to the number of points in that first category divided by the total n. Okay? That actually makes sense, and we could have guessed this. Now, what if the alphas are not 0? Well, we end up with exactly the same scenario that we dealt with earlier in working with the coin flips, is that we have sort of this hyperparameter dependence here. Now, as the number of outcomes n1 and as the total number of outcomes n1 plus n2 plus n3 becomes very large as compared to the alphas, which are fixed as a function of data points, then eventually we see this result eventually converge in the large n limit to n1 over n, which is what we would have anticipated. There is one point that's worth mentioning here, and it's that if I have very many different categories, then eventually what I find is that the probability of predicting that something belongs to a particular category actually shrinks. And that's an interesting concept because it's sort of, revealing, or it's hinting at the fact very preliminarily that the more complicated I make a model, the more difficult it becomes, or the more reduced the probability is in predicting that the next data point belonged to a particular category, just because I have a lot of categories to select from. So it's hinting at something very important, which maybe I can say in just a second, and we will explore sort of in the context of more complicated or more elaborate examples later, is that the more complex I make a model, the harder it becomes to predict subsequent data points. On the other hand, the more complex I make a model, typically speaking, the better I can fit the existing historical data. So somehow in predicting, I need simple models because otherwise it becomes more difficult to predict, and my probability of predicting that a data point falls in a particular category kind of drops. But on the other hand, predicting historical data or fitting historical data, in some sense, the more complicated you make the model, the better you're fit to the data. You still have to be a little bit careful because the best model to fit the data is really something that sort of fits every data point perfectly, which at that point is not really a model anymore. It's just an interpolation between every data point. So if your goal is really to use your model for the purposes of understanding and prediction, then there has to be some degree of simplicity to your model. So with that said, we've just covered sort of two very simple examples. One was the case of a coin flip, and the other was the case of three different options, considering sort of three different options. We did see kind of an interesting phenomenon emerge, which we didn't emphasize too much, but we will delve into in detail next time, which is the notion that by virtue of choosing the priors that we did, multiplying the priors by the likelihood resulted in posteriors which had the same mathematical form as the priors themselves. And that notion lends itself, or leveraging that notion lends itself to very efficient computation. So if every time that I add a data point, or I consider a new data point, the mathematical form for my posterior changes, then computationally I will start having some problems. Ideally, if the shape for my distribution kind of stays the same, so I take the prior, I multiply it by one data point, I get the likelihood from one data point, and then I keep on accumulating information, and the mathematical shape for the function for the posterior stays the same, then I can start leveraging that for computational efficiency. So that's going to become a very important point that we will delve into in much more detail next time. Thank you.